So, a topic I struggled with in organic chemistry this semester was when cyclohexane went from being two-dimensional to being three-dimensional in its chair formation. I struggled with how that related to the two-dimensional, just hexagon, and where the substituents would go in relation to that. So especially this was troubling me with cis and trans, and I didn't know how it correlated to axial and equatorial on the cyclohexane chair. And so cis and trans, cis is when you have two substituents that are both in the same plane, versus the opposite, which is trans, which means you have two substituents that are in opposite planes. So one would be sticking out of the page, the other would be sticking into the page. And on cis, they'd both be sticking out of the page or both be sticking into the page. And with axial and equatorial, axial on a cyclohexane chair is the axial groups are the ones that are in the vertical plane, whereas the equatorial groups are the ones that are in the horizontal plane. Now, the equatorial groups are much more stable than the axial groups. So your largest substituent in the equatorial groups. And at first, I thought there was a correlation between the cis isomer and whether it was in the axial or equatorial position. And turns out I looked that up and it's much more simple than that. So with cis, since they both have to be in the same plane, it doesn't matter whether or not they are in axial or equatorial. All that matters is that it is both sticking up from the carbon they are attached to. And same way with trans, they're supposed to be out of plane with each other. So one substituent sticks up, one substituent sticks down. You just have to make sure that if it's in the axial, it's up, and if it's in the equatorial, it's up as well, versus the other substituent for a trans molecule would be down, whether or not it's an axial or equatorial. And other topics that I found difficult are radical reactions and synthesis problems.